So the little theories actually work really well. I mean, it tested the theories that we had with lots of random inputs, and it never found a counterexample. So it gives us really good reason to believe that it probably works. But even better than that is to actually prove that it always works, and that requires a theorem. So here what I have is a theorem that says that if n is a natural number, then in fact if I take n and I convert it to a list of numerals, and then I take those and I convert it back to a number, I get back n. Okay, and this works for natural numbers. Now remember, ACL2 is a theorem prover, not just a programming language. So we can actually submit this theorem to ACL2, and it will use induction and try to prove this, and in fact it succeeds. It says yes, that's always true, which is great. Okay, now let's go the other way. Okay, so what we'll do is we'll say, suppose that L is a list of digits, and let's suppose that L does not end with a 0, which means that 0 is not the leading digit of the actual numeral representation. Okay, so if I take that list and I convert it to a number, and then I take that number and convert it back to a list, I should get back L, right? This is, remember, we tried this with lots of random lists, and we never ever found a problem. But if you actually try to prove this, you don't succeed. Okay, the ACL2 theorem prover is just not good enough to be able to prove this by itself. Okay, so this fails, and even worse than that, it fails after a very long time because it really tries hard. Okay, so let's see what we can do. Okay, now when you, I won't actually ask you to use ACL2 to this level. Okay, but I just want you to see the way that that ACL2 is used in practice. Okay, so ACL2 fails, and when it fails, it tries to give you some information as to what went wrong. And it does that by giving you a checkpoint, okay? So as it's proving things, right, it actually needs some lemmas as it goes along. And it looks at each one of those as a checkpoint that says, I'm about to do something interesting, so remember this spot, okay? And here's one of the checkpoints. I've actually cut out a lot of the information to just kind of come to the part that we need, okay? So here's what we have. We have that L by itself, right? There's no conditions on that. That just means that L is not nil, okay? So L is actually a list that has something, right? And here's the induction hypothesis, okay? The induction hypothesis is that if I take everything except the front of her, CDR is actually the same as rest, okay? So if I take everything except the first element of L and I convert that to a list of digits, okay, and then I turn it around, I should actually get back the rest of L, right? Okay, this is the induction hypothesis what we're trying to prove, right? Okay. Oh, and we have that the rest of L is actually a list of digits. Again, this is all part of the induction hypothesis. Now let's look at the conclusion that we need to have. What we need is that when 10 is multiplied by whatever the rest of L is converted to a number, I should get back an integer. Well, excuse me a second. Isn't that just always true? I mean, forget the induction hypothesis, right? I don't need it. It should just be the case that if I take a list and I I convert it to a number, I should always get back a natural number, right? Because of the way we wrote it, right? And in fact, if I take a natural number and multiply by 10, I get another natural number. So this should just always be true, okay? Regardless of what these hypotheses, right? These are actually not needed, right? They're a distraction. And that's kind of what's happening. In fact, you see those dots, and you see that there's a lot more hypothesis that ACL2 has at that point. And it's just getting lost. This losing fact of the actual important fact, which is that this should always be an integer, right? So the way that we solve that is we have to prove some lemmas. Okay, so here's the lemma that we want to prove. And the lemma that I want to prove is that if L is a list of digits, then in fact, when I convert it to a number, I always get back a natural number. Okay, now if ACL2 just knew that, okay, then right here, what it would say is, oh, this is a natural number. And it already knows that if you have a natural number and you multiply by 10, you get back a natural number. And every natural number is also an integer, so it'll just go, oh, easy. Okay, which is actually what you and I would do, right? We just look at it and go, well, that's obvious. Okay, so that's That's the trick, okay? So we proved this, okay? And by the way, ACL2 can prove this automatically, right? By induction. And once we prove this, then the other theorem should go, right? Let's see. Of course it doesn't, right? This is very common, right? This is just the way that we prove things. Whether we do it by hand or we do it with the help of a computer. We put something out there and we keep trying and then we go, oh, it still fails. Why doesn't it quite work? And then try to learn from that. So here's what's happening now. Okay, here's the new checkpoint. You know, when I submit the theorem after adding that lemma, this is what comes up as the new first checkpoint. And shoot, that looks absolutely complicated, right? Okay, so you might say, I don't really know how we're gonna find this. Okay. Except there's a couple of things that you might notice, okay, and that's what we do. We just look at this and try to notice things. So, for example, here's this. Okay, that is the remainder after I divide something, right? Here it is, by 1. So what should the remainder be? Well, excuse me, if you divide any number by 1, the remainder is always 0. Okay, so that should just be equal to 0. Okay, I mean, it just should be, right? Now, once that turns out to be equal to 0, then 10 times 0 is just 0. And then minus 10 or plus, you know, the first element of L, car is a synonym for first. Okay. Well, yeah, that's actually what I want. Okay. So maybe that should be equal to something. Okay. So that's the first step. Okay. I noticed something that looks a little funky there. Okay. I might find something else that looks a little funky. Look at this. Floor of digits to number, right? And this just goes on here. 1. What should that be? Well, that's the quotient when I divide that thing, right? That's when I divide this by 1. Well, the quotient is just that, right? If I divide 10 by 1, the quotient is 10, the remainder is 0. So maybe you should know that fact as well, right? Those are little things that ACL2 hasn't been able to simplify, and that's what gives me, as a long-term user of it, a clue that it just needs one more lemma to get it through. So let's try that. Okay. We proved those 2 lemmas. And by the way, again, once we state them, ACL2 looks at them and goes, well, that's obvious, right? Which I always find ironic, because it's not like it comes up with them by itself, but it recognizes them as true, right? That's the part of that human brain that we have that is really, really useful. It's the part that does creative ideas and that knows how to solve problems. So yeah, ACL2 now says, yep, actually, I believe that's true. And then when we submit our second property, ACL2 goes all the way out and says, yeah, I knew that all the time, QED.